In this video, we solve 15 integrals as efficiently as we possibly can. Rather than using formal u-substitutions, we just casually use the chain rule backwards. We take advantage of symmetry in any case where we possibly can, and we take advantage in one example of the periodicity of a function to shortcut the work. So let's get started. In the first integral, I have an indefinite integral of the square of the secant function. This just means give me the antiderivative, and that's the tangent function, and we're done. Second integral, I notice that I have an integration interval symmetric about the origin and an even function in the integrand. So I can write this as twice the integral over half the interval, and I guess the antiderivative, and I get a 1/3 x cubed, just adding 1 to the exponent, dividing by the result. And I evaluate from 0 to 1. And the payoff for recognizing the symmetry here is in that lower limit. If I sub in 0, the result vanishes. When I plug in the upper limit 1, I get a 2/3 times 1 cubed, or 2/3, and I'm done with that one. In number 3, this -3 is a spectator, and then I need to guess the antiderivative of the sine of 2x. Well, that's essentially cosine of 2x, but if I imagine differentiating cosine 2x, it gives me, first of all, a minus sign, and then a sine of 2x, and then the chain rule kicks in and tacks on a factor of 2 to that. So I need to prepare to cancel that 2 with a 1/2 out in front. And again, the most general antiderivative has an arbitrary constant in it, and this simplifies to 3/2 cosine of the quantity 2x plus c, and we're done with that one. In number 4, I have another indefinite integral. In this one, the standard approach is to rewrite it as a power function, x to the -3. I add 1 to the exponent, divide by the resulting number. That gives me an x to the -2 divided by -2, or a -1/2 x to the -2 plus c. And I clean it up as -1 over 2x squared plus c. And number 4 is done. In number 5, I see an odd function integrated on an interval symmetric about the origin. That means the function spends just as much time above the x-axis as it does below, and this one vanishes by symmetry. In number 6, I notice that again I have an interval symmetric about the origin, so I start looking for symmetries to take advantage of. And x squared plus 3 is an even function. X minus 1 is not even or odd. It has some of both. And so what I'm going to do here is distribute the x squared plus 3 over these two terms. And now this first chunk is a product of an odd function and an even function, and I know that that gives me an odd result. So if I split off that chunk as a separate integral and integrate from -2 to 2, I know the result is going to vanish, so I can ignore that whole piece. The other piece, this negative x squared plus 3, that's an even function. I'll pull the minus sign out in front, and I know that when I integrate an even function on an interval symmetric about the origin, I can just take twice the integral over half the interval. Now I guess antiderivatives, so I add 1 to the exponent on x and divide by the resulting number, and then the integral of 3 is 3x. And again, we enjoy having zeros because when I sub in that lower limit, both terms vanish, and I don't have to worry about that. Sub in the upper limit, and I get 1/3 2 cubed, or 8/3, plus a 3 times 2, which is 6. 6 is 18/3, so this gives me a total of 26/3 in there. And my final answer is -52/3. Moving on to number 7, the standard approach to this thing is to express that integrand as a power function. That's at x to the -1/2. Then I can use the power rule. I add 1 to the exponent and divide by the resulting number. Dividing by 1/2 is the same as multiplying by 2. And x to the 1/2 can be written as a square root of x. Then when I sub in the upper limit, I get 2 square root of 2. Lower limit, 2 square root of 1, or simply 2. And we're done with that one. In number 8, I'm asked for the antiderivative. Now I could have written this as an indefinite integral. I just wanted to mix up the notations. But I want the antiderivative of cosh of 3x. And I'm going to use the standard notation here and call that a capital F of x. And the antiderivative of cosh is basically sinch. But if I stop there, I'm in trouble because differentiating sinch of 3x would give me cosh of 3x, and then the chain rule would tack on a factor of 3, the derivative of the interior function. So we adjust for that by putting a 1/3 out in front. Don't forget your plus c. And we're done with that one. Number 9 is the standard trick of re-expressing as a power function, using the power rule, and then just cleaning things up a little bit. So dividing by 3/2 is the same as multiplying by 2/3. And that one's done. And in number 10, I do the same thing. I prioritize expressing this as a power function. The 1/5 can be pulled out as a spectator. My integrand is now x to the negative 3. I add 1 to the exponent, divide by the result to get the antiderivative here. And that gives me an x to the negative 2 divided by negative 2. And I'm evaluating from 1 to 2. Pulling that negative 2 out in front, I end up with a negative 1/10. And then I'll rewrite my x to the negative 2 as 1 over x squared. Now I can sub in my upper and lower limits. And 1 over 2 squared is 1/4. 1 over 1 squared, that's just 1. And in those parentheses, 1/4 minus 1 is negative 3/4. Multiplying that by negative 1/10, I get 3 over 40. So in number 11, this requires that I recognize the formula for the derivative of an inverse tangent. The derivative of inverse tangent is 1 over 1 plus x squared. So my antiderivative of 1 over 1 plus x squared is an inverse tangent of x. Don't forget your plus c, and you're done. In number 12, again, I have an interval symmetric about the origin, negative pi over 2 to pi over 2. And so I start thinking about parity issues or symmetry issues. And I see an odd function, the sine function, multiplying an even function, the cosine function squared. And I know that an odd times an even function gives me an odd result. And the integral of an odd function on an interval symmetric about the origin vanishes, and we're done. In number 13, I have an indefinite integral, in other words, an antiderivative of cosine of 2x. And this is essentially the sine of 2x. And then I start adjusting. If I were to differentiate the sine of 2x, I would get a cosine of 2x, but then the chain rule would say you have to multiply by the derivative of the interior, which is 2. So to make up for that, we prep this term with a 1/2 out in front. Now I have the thing that I differentiate to get the cosine of 2x, and we're done. In number 14, I have an indefinite integral again, and I can pull that 5 out in front as a spectator. And so I'm just trying to guess the thing I differentiate to get e to the negative x. And it's basically e to the negative x, but if I differentiate e to the negative x, I get e to the negative x multiplied by negative 1 because of the chain rule. We can cancel that factor by putting a minus sign out in front. Now try it out, and when you differentiate, you get what you started with. We clean things up just a little bit, and I get negative 5 e to the negative x plus c. And we're done. And finally, we get to our 15th integral, and I have the sine of 2 theta integrated on 0 to pi. And rather than use brute force on this, I recognize that something is going on with periodicity. The period of this sinusoidal function is 2 pi divided by the coefficient of theta. In other words, the period is pi. And that means this sine function completes exactly one wiggle on the integration interval, which goes from 0 to pi. And that means it spends exactly as much time above the theta axis as it does below, and the integral vanishes. If you enjoyed this video, or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.